here, like, see, here's the lambda, we do the division, and we get this answer for the frequency. But we want it in gigahertz. So instead of 10 to the 14 hertz, we have to move the decimal over 5 places, this number. And then we replace 10 to the 9 hertz with gigahertz, and we get here. So
Okay. So, anyone get the answer yet? Like on their own?
Yeah.
Okay. Is anyone else able to calculate and get the same number? Okay, awesome. Okay, let's do another one.
the energy of the photon has a frequency.
So now we're talking about the energy of the photon that is at a frequency of 110 gigahertz and they're actually going to give us, some stuff. So E equals HF, H equals Planck's constant. I always like to remember that because you build a house out of Planck's. It's like just the way I remember it. I mean, it's a silly way. Like, it's not a P, it's an H. And F frequency is easy. So this, you could look this, now if you want to look up Planck's in joules, you could actually look it up online. They'll give it to you. Or you could look it up on the web. So look on the web if you have a computer right now, look up Planck, and this number will come up. Look up Planck's in joules. And tell me, raise your hand once you get this number.
That one is us, J minus.
Yeah, the joules is set, the joules per second, and joules per second, we know, the joules, what do we know that is? Let's do the frequency. Frequency has to do with this. So the energy of a photon that has a frequency of 110 gigahertz is, I mean, it basically gave us the answer, but I want you to be able to calculate. Well, yeah, I know it gave it to you, but I want you to be able to calculate it. So did anyone at least get the first part? Did anyone? When you actually raise your hand when you're able to get this on the web. I just want you to go to google.com and type in Planck's. Planck's in joules, and I want you to see if you can get 6.3 times 10 to the,
Planck's in
It
joules.
says 6.62.
I got it.
76.76.
Okay, so it gave it to you. So Ramina found it. Anyone else? Anyone not find it? You didn't. Oh, you're on your phone, so that's why.
I didn't find it.
What?
I didn't find it.
Ramina, can you show them how to find it?
How'd you find it? I just searched up Planck's and joules, and it's the first website that showed it. It's like, okay, it's right there.
And guys, why did we do 10 to the 9? Can anyone tell me why we did 100? Well, we know 110 because right here, but why did we do 10 to the 9?
Because gigahertz goes to the thing.
Yes, exactly. And then, so this, we got on this number, this is an equation, energy equals Planck's constant times the frequency. They give us that constant, they give us that equation. Again, Planck's constant to the joule, we find that online, so we don't have to memorize that. And then we have this, it's basically given to us, and we know 10 to the 9 is a gigahertz. So it's really not that hard. It looks hard, but it's really not that crazy. Okay. And then
Times 10 to the minus 23rd joules. The answer is
there we go. Okay. And let's go to the next one. And then we have another, 15 minutes? So we're pretty good on time. Okay, the frequency of a photon that is an energy of 3.7 times 10 to the negative 18 joules is, hold on 1 second, let me just get you the formula sheet. Just paste it. Okay, see if you can work this out on your own. So the frequency of a photon that has an energy of 3.7 times 10 to the negative 18 joules is, and we know that how did we get the energy? Once talk in your groups for like a minute or two, see if you can discuss how we got these different numbers to plug in. Remember, Planck's constant is a what?
Constant.
It's a constant, and constants are given to us. So we don't have to remember the constant. I mean, if you want to, that's great. It helps you, but you don't have to. So, so the energy, 3.7 times 10 to the negative 18 joules, how did we get that? Who wants to tell me? Ramina? It was given, right? And guys, this we just flipped around. It's just like regular algebra. 6.63 times 10 to the negative 34th. How did we get that? Who wants to tell me? Who wants? What do you think? It's given. It's the Planck's constant. Okay, it's given to us, right? Okay, and then when we get 5.6 times 10 to the 15th, how do we get this answer? What's 18 minus negative 34?
15.
51.
Yeah, that's it. 15. So we just minus the exponents and we got the 15, and we divided this out and we got 5.6. That's how we did it. Okay. And remember, I'm sorry, this is the part that the joules is very important. Do you see how the joules cancel out? Because there's a joule here and there's a joule here. So we just have the S, which is, per second is going to be hertz, right? Remember, hertz is like how many refreshes per second, like on the TVs, like what's the frequency per second? And so that's why the answer is showing right here. Hertz, okay? And we see seconds, so we see hertz. Whenever we think of hertz, think of second. Just like when you buy the TV, the refreshes per second gives you a better image on the TV. Okay, glad we got that one. Let's do question 5. And you can work in your groups. The energy of a photon that has a wavelength of 12.3 nanometers. Why is it nanometers? Because it's, what do you measure in nanometers? In color, very good. Okay? So, energy equals hc, Planck's constant, times the speed of light over lambda, which is the wavelength. So, right now they gave us 12.3 nanometers, which is great. So 12.3 times 10. Well, why did we go 10 to the negative 9?
Gigahertz is negative, isn't 9 to the power.
Because you're converting from nanometers to something else.
Because whenever we're converting, yeah.
I have a question.
Sure, what's up?
Why is the 12.3 on the bottom and not, like, it's flipped? Because usually 6.6 times like that is on the bottom.
Well, if you look, we have energy equal, because they're asking us to find the energy, right? So we're always flipping around this equation, right, through algebra. And so right now we have energy. So if we flip it around to get the energy, you have Planck's constant over lambda. And then it's saying 12.3, which is, remember, lambda has to do with the wavelength, and wavelength is usually like nanometers, right? I mean, with the colors, usually nanometers. So then that's why you just see 12.3 gets brought down to the wavelength, and then you do times 10 to the negative 9 meters, because we're going from nanometers to meters. So then we have to, that's why. Okay, so whenever you do unit conversions, you're moving over the decimal either to the left or to the right, depending on what you're doing. And then from there, thank you, Kamina, for showing her.
Frequency is speed of light over lambda, right? So when you have
Okay,
energy equals
and then we know Planck's
Planck's
constant
constant
is given
is
to us, 6.63 times 10 to the negative 34 joules a second, right? Well, which two are going to cancel out here? Remember, if you have like, 5 apples divided by, 5 apples, you're going to cross out the apples, right? So what are you going to cross out here? You're going to cross out the meters, very good. Okay, so if you just have this, okay, so then we're just going to be left with the joules. Okay, and then that's it. So 6.63 times 10 to the negative 34 times this. Was anyone at least able to get this answer, like at least on the calculator? Keep working on it until you're able to get it. Yeah. I'll give you another minute or two. It's confusing? Well, who here doesn't find it confusing? Okay, Carmina, why don't you explain it in a way that's not confusing?
So, beginning with the equation, we have the formula for,
Here, Carmina, take this. You can use the laser pointer.
okay, so why this has changed is because we're dealing with wavelengths, not frequencies. So the formula for frequency is frequency equals the speed of light over lambda. And so it's normal energy is Planck's constant times frequency, which is h times the speed of light over lambda. Does it make any sense? Yes. Lawrence?
If you memorize the equation, or not even memorize the equation, the formula, if you see the formula, just flip around the formula.
Frequency is speed of light over lambda, right? So we're just replacing frequency here by the speed of light over lambda. So it's Planck's constant times the speed of light over lambda. Okay, and then so we have Planck's constant, which is 6.63 times 10 to the negative 34, which is already given. And then we have the speed of light, which is a constant as well. And all they give us is this, which is lambda wavelength. So we're just plugging in the information that they give us.
Okay. You're just plugging it in, that's really all it is. And the only thing that's like maybe complicated about this will be that you're converting from nanometers to meters. And when you do that, just remember that you go into the -9, right? And I mean, that's the most complicated thing about this. You can watch the video again if you need help. I'll even play it if you want.
Let's use our equations here. It's hc over lambda, where h is Planck's constant. Notice here we're using the value of Planck's constant, joule seconds, not electrons.
And remember, you can always look up online what is Planck's constant in joules, and we'll give it to you.
Seconds. You can find it on the web, or do a translation, where 1 electron volt is 1.6 times 10 to the -19 joules. So we're just going to put the value in the joule seconds. Here's the speed of light. Here's our wavelength. Notice how we've shifted from 12.3 nanometers to 12.3 times 10 to the -9 meters, because we always want to work in SI units. We get an answer of 1.62 times 10 to the -17 joules. The answer is D.
Okay, this is the last question, and then we're making good time. Okay. If the wavelength of a photon is half, by what factor does its energy change? I'm going to give you a clue by pulling up this. Okay, so try to figure it out. Work in your groups.
what factor is it?
I know this one's confusing, but when you really think about it, it's not. Yeah, but why is the answer there? Why is the answer what it is? I want you to look at the answer and I want you to explain it to me why it's there. So talk in your groups,
Okay.
and who could translate this to me in a way that makes sense to
Energy.
you?
Since E equals energy.
Talk to your partner.
And 2
Talk.
is energy.
Carmina,
That's a
go around and see if anyone Remember, E is the energy, H is Planck's constant, C is the speed of light divided by lambda, sorry.
I understand this is
We're just flipping it around.
Kind of puzzled. Is that even a word? Hold on.
We're just plugging it in, right? You should at least have our for example, like it's given to us.
It is a word.
Planck's constant.
Really? Yeah, someone told me it wasn't.
Right? Now we plug it in and we do
It's confused, basically.
light over lambda divided by 2.
So I did this
Say,
alright.
when the photon is half, we know the photon has to do with lambda, so light. So when we just plug that in, we reverse it around.
But this is easy. This I get, but the other one I don't.
So 2 E's just shows that
So,
it's.
how was your day?
That's it.
I just started it. I don't know.
Alright, so Marcelino didn't understand, now he understands. What, do you want to explain it?
So it's like inverse operations, so like first, substitute and put it in the variables.
Okay.
So, after like, the one inverse operations, you're eventually gonna make it back to 2D.
That's it, you got it. Good job. Thank you for sharing. That's it. So guys, a lot of this stuff seems complicated, but it's really just plug and play. That's how I like to think of it.
This is easy. The other one not really.
Alright. So this is part 7. And let's oh my god, let's get to this. Okay, so hydrogen is simplest because it has the least amount of orbitals, right? It gets more complicated as we get more orbitals. But remember this,
It's the
so
rainbow.
you can see neon. You can see the spectrum colors of neon when and then we can see sodium right here. And so I want to just show you, okay. So we have, this is hydrogen absorption and hydrogen emission. So hydrogen absorption is when white light hits it.
I heard of it.
Okay, when white light hits it, it's going to absorb different colors. Because white light is made up of,
Multiple colors.
yes, okay, white light. Yeah, emission is when it gives off. Okay, so when hydrogen gives off, hydrogen is just going to give off purple or blue or turquoise or red. And you notice that the absorption and the emission are always opposite. So when you get red here, you get black. When you get turquoise here, you get
Black.
when you get blue, you get
Black.
purple.
Black.
This, right? And when you get colors here, you get
Black
black. It's
and
that simple. It's just the inverse. It's the opposite. So yeah. So any element, their absorption spectrum and their emission spectrum is the exact opposite. Because absorption is the exact opposite of emission. And that's pretty much. Hey, how you doing? Okay. And here you go. Now when it gets more complicated, when you get to iron, which is Fe, right?
That's what my screen looks like every time I
You're not doing that. It's like a barcode. You're not memorizing the barcode. No. But I think you can just see it. It's more complicated. Look, because hydrogen is just going to have two colors. Iron, look how many colors there are. It's wild, right?
I'm colorblind.
You're colorblind, it's hard, right? But, okay. What is that?
I'm genuinely colorblind.
So who can tell me, guys, why does iron have more? Why does iron have more spectral lines? I gave you some help by putting the answer wide up on the screen. On 3,
That's
1,
more
2, 3,
electrons.
why?
It has more electrons.
More electrons. The more electrons, the more
More
light, because the light is doing what?
emission.
Yes, more opportunities for it to.
What do you say? What do you
Drop.
drop. So you got it.
Let me hear him
Now-
the last question. Oh,
Okay.
moving on. Yeah.
Okay. Let's go, let's just try to get to the. Okay, so the emission spectrum for chlorine, Lawrence, the emission spectrum for chlorine is shown below. Which of the following represents chlorine corresponding absorption? Remember that they're giving you this. What is this?
The spectrum.
Is this absorption or emission?
Oh.
Okay, so which one's going to be the absorption? I mean emission, I'm sorry.
B.
Exactly.
Really?
So the answer is B.
It's very good that you're able to
You're
see it.
right.
Even though you're colorblind, you're able to see it.
I didn't say. No, you didn't say
Who is colorblind?
I'm not colorblind, he's colorblind.
Oh, okay, then that's gonna be hard for you, so that's gonna be difficult, actually. I don't know the answer to that.
I can see the color.
You can see it? Okay.
Yeah. You see the
So
color.
you're not
It's gonna
colorblind.
be colored by test.
So how are you gonna remember that, absorption?
It's the opposite.
Wait, she sees the colors differently, she just told me the opposite, right?
And how are you gonna remember that
Really, bro, all I know is that the opposites are black, so whenever I see the color, I say the opposite is black. So,
Okay, great.
and then whenever there's black, I say it's opposite. I really don't care.
Very good, good enough, great.
Colorblind was the picture below.
So this is, so guys, when it's dropping, is that absorption or is that emission? I want you to go like this. 1, 2, 3, 4. I'm closing my eyes. You can ask your partner.
No.
3, 2, 1. Let's see. Ready?
To me.
Very good. If you're giving off, you're emitting.
That makes
If
sense.
you're jumping up, you're absorbing.
I got the
Okay?
I think should I show it again?
Last one. What time do we? 9? Okay, we have 2 minutes. Guys, shh, we have one more. Ready? So, which of the following is not true regarding the Bohr model of the atom? Put up your fingers. A, B, C, or D. Is it A? Electrons could exist only in a certain quantized orbits around the atom. Is it B? As n becomes greater, the energy of the orbit becomes greater also. Is it C? When returning from an excited or emotional state, I guess. An electron can only move between the set of Bohr orbits, or D, all the above are true. Let me see, A, B, C, or D. Let's see, fingers, whatever you think. Not showing.
I was right. Oh, I was right. Oh, I was right.
I see fingers jumping up and down. What do you think? What do you think, Mimi? You think you're all true? I think you're all. I think. Let's see if Mimi's right.
Oh, I
Okay,
was
Mimi had a great
right.
answer. So
That is as stupid as I thought.
they're all not true. Okay. As n becomes greater, the energy of the orbit is greater also. Is that true? It's saying which of the following is not true regarding the Bohr model. As n becomes greater, the energy of the orbit. And does the energy become greater?
Yeah. This is the answer. No, it's this. It goes from this to this.
That's a good point. So let me hear this.
It goes from this. Wait.
Oh, okay. I thought it said all. Yeah, you're right. They're all true. I thought it said none of the above are true, which was 32. You're right.
No,
Okay,
all
they're
of
all
these are
true,
true.
obviously. So as n becomes greater, they become closer to 0, and obviously that means they're greater. Okay. Electrons can only exist in certain quantized orbits around an atom, obviously. And when returning from an excited state, an electron can only move between the set of 4 orbits. Exactly. It can't go into the light. It can't
I
go.
did that to a baby and he
Exactly.
started crying.
Simple.
I did this to a baby and he started crying.
Last but not least,
Alright.
we have number 8, and then we finished the 4th portion of the yeah.
Number one.
So Bohr's model answered a lot of questions, but it still had some problems. So the Bohr's model was better than some of the previous versions, such as J.J. Thomson or Democritus or any of those ones. Now, we had problems because there's two problems that you have to know. Multi-electron atoms did not have the energy levels predicted by the Bohr model. Okay? Let me read that again slower. Multi-electron atoms with multiple electrons, did not have the energy levels predicted by the Bohr model. Okay? So it was good for hydrogen, but not for the more complex ones. Double and triple bands appear in emission spectrum. The model does not have an explanation for